You ever stop and think about that? I mean, what could a massive high-speed train possibly have in common with that tiny little buzz in your pocket? It sounds kind of impossible, right? Well, it turns out they're both powered by the very same invisible forces. These things are all around us, just running our entire world in ways we barely notice. So today, let's make the invisible visible. Welcome. In this explainer, we're going to pull back the curtain on the magic of electric machinery. We're going to dive into the core ideas from one of the most foundational textbooks on the subject, and you'll see just how these concepts leap from the page and into the gadgets and gizmos that shape our everyday lives. So, here's our game plan. First, we'll get to know the two most important invisible forces. Then, we'll see how they work together to create motion. After that, we'll meet the big families of machines they power, give a little spotlight to a crucial unsung hero of our power grid, and then, to wrap it all up, we're going to crack a real engineering problem together. Sound good? Let's go. Okay, let's get right to the heart of it. You know, everything we're about to talk about, and I mean everything from giant power plants to your smartphone, it all boils down to a surprisingly simple dance between a piece of wire and a magnet. This right here is the first of our two superstars, induced voltage. You've probably heard it called Faraday's law. And put simply, it just means that if you've got a wire and a magnet and you change their relationship, move one past the other, you can literally create electricity out of thin air. The process itself is just beautiful in its simplicity. So you start with a magnetic field. That's just that invisible area of influence around any magnet. Then you take a wire and you move it through that field. And that simple action induces a voltage. Think of voltage as the push that gets electricity moving. That's it. In that one moment, you've created the potential for power. Now, here's why that simple little idea completely changed the world. This exact process is at the core of pretty much every power plant on Earth. It doesn't matter if it's a hydroelectric dam, a nuclear reactor, or a coal plant. They are all just incredibly complex ways to do one simple thing: spin a wire inside a magnetic field. It is literally the engine of our modern world. So we can turn motion into electricity. Pretty cool. But what about flipping that around? Can we use electricity to create motion? You bet we can. And that brings us to our second key principle. And here it is, our second superstar, the perfect partner to the first one. It's called induced force. This time, instead of us moving the wire, we push an electric current through a wire that's just sitting inside a magnetic field. And when we do that, the magnetic field pushes back, creating real physical motion. And this is the secret behind every single electric motor. That buzz you feel when your phone vibrates, that's a tiny motor doing this. The giant powerful engines that push an electric car down the highway, it's the exact same principle, just on a much, much bigger scale. It's all about current meeting a magnetic field and making things move. So there you have it, the whole picture. These two ideas, induced voltage and induced force, are like perfect mirror images of each other. They're two sides of the same coin. One turns motion into electricity, that's a generator. The other turns electricity back into motion, and that's a motor. This simple, elegant little partnership is the foundation for everything that comes next. Okay, so now that we've got the basic physics down, let's meet the two major families of machines that are built using these principles. Now, of course, taking these really neat theories and putting them into practice, well, that's where the real engineering adventure begins. We're making the leap from the textbook concept to the real-world stuff. And when we do, these principles give us two main families of machinery, AC and DC. Yep, those two families are AC and DC. The easiest way to think about it is this. Alternating current, or AC, is the workhorse of the grid. It's the power that comes out of the outlets in your wall and runs the big, heavy-duty motors in factories. Direct current, or DC, is the power of things that move. It's that steady, reliable flow you get from a battery, and it powers everything from your laptop to all the electronics in your car. Two different jobs, two different kinds of current. But hang on, there's another crucial piece of equipment out there. It's not a motor, it's not a generator, but honestly, without it, our modern world would just grind to a halt. The absolute best way to picture a transformer is to think of it like the gearbox in your car, right? A gearbox changes the speed and the torque of the engine's power. Well, a transformer does pretty much the same thing for electricity, but instead of speed and torque, it changes voltage and current. And what's just mind-blowing about these things is that they do it with absolutely zero moving parts. It's a totally solid, static device. It just sits there and uses those very same magnetic field principles we just talked about to change electricity from one level to another. It's like magic. So why do we even need to do that? Well, because it's way, way more efficient to send electricity over long distances at a super high voltage. So transformers step up the voltage at the power plant for that long journey across the country. And then a whole bunch of other transformers step down the voltage right before it gets to your house so it's safe to use. They are the quiet, totally essential heroes of the power grid. All right, enough theory. We've covered the big ideas. Now let's see how engineers actually use this stuff to solve real problems. Time to roll up our sleeves. Okay, I know, this might look a little intense, but don't worry. Think of it as a puzzle. It's just a roadmap for where electricity is supposed to go. We're not going to get bogged down in every single calculation, I promise. But what we are going to do is understand the logical steps an engineer takes to solve for one little piece of this puzzle. So here's the mission. We know what we're starting with. Our power source, the input voltage, is 12 volts. Our goal is to figure out the output current, basically how much electricity is actually flowing through that one specific part of the circuit at the very end. And again, without getting lost in the mathematical weeds, the process itself is actually very methodical. Engineers apply a few basic rules to describe how electricity moves in each little loop of the circuit. This gives them a set of equations. And from there, it's really just a matter of using some algebra to solve for the one thing they're looking for. In our case, that output current. And after running through that process, boom, there's our answer. The output current is 0.158 amps. We've cracked the code for this circuit. But you know what? The number itself isn't even the most interesting part. The real takeaway, the really beautiful idea here, is something called the Linearity Principle. All it means is that for a circuit like this, if you double the power you put in, you get double the power out. It's perfectly proportional. And that isn't just a neat math trick. This predictability is the absolute bedrock that allows engineers to design incredibly complex systems because they know exactly how they're going to behave. So, there we have it. We've gone all the way from a simple magnet and a wire to solving a real engineering circuit. We've seen how just two fundamental forces are basically the source code behind almost every piece of electric machinery we rely on. So that leaves just one question. Now that you've seen this code, what other invisible forces shaping our world are you ready to understand next?